Okay, in this video, we are going to continue talking about physically based rendering. These are just wrapping up some concepts that weren't covered in the first video that are particular to some of the things you guys are going to be encountering when you work with shaders in our offline rendering programs like RenderMan. So continuing the conversation of specularity, we have both isotropy and anisotropy. So most materials are isotropic, or the reflections are isotropic. What that means is that there's no particular directionality to the reflections. There is, of course, the shape of the object is going to be changing the shape of our reflections or the perceived shape of them, but for the most part, the surface isn't changing the directionality of a particular direction or favoring a particular direction for our reflections. An anisotropic object will reflect specular lights in a preference towards a particular direction. So you can see on the left-hand side we have an isotropic sphere, and on the right-hand side we have an anisotropic, and you can see there's like a favored direction that is reflecting the light in. So these light reflections are usually caused by parallel linear grooves on the surface. So the reflection appears to stretch perpendicular to these grooves. So you can see down here we have this brushed metal iron pot. And because of those linear brushed metal grooves that are going in the circular shape, you can see they're stretching our reflections perpendicular to the direction of those grooves. So you'll see this on things like CDs, brushed metal, feathers, certain fabrics, and hair. So here's some examples. Anisotropy refers to the directional patterning or stretching that appears in the reflections on some surfaces. So on this hair, you can see on her skin, on her face, all these reflections are more or less not favoring a particular direction. They're just based on the surface shape of the object pointing at the surface. In this case, the hair is actually stretching and favoring a particular direction for the reflections, which is causing this linear band that goes across right here. Same thing with these reflections on this record, right? You can see it's stretching these horizontal reflections because of these linear grooves. And you can see in both cases, it's perpendicular to the direction of those grooves. So this is going this way, the light stretches this way. These are going this way, the light is stretching this way. And here's just some more example. And so this stretching is caused by the surface having, most of the time, linear grooves or peaks that are parallel to one another. So the direction that the reflections are stretched is usually perpendicular to the direction of these lines. So you can see I have a single cylinder. I just mocked this up in 3D. You can see this is pretty much uniform in all directions. There is a bit of a shape distortion that's causing this to kind of be stretched vertically. But you'll see when I take this cylinder and I put a bunch of them next to each other, it almost gives the perception that this has a stretched singular reflection or horizontal reflection this way that's perpendicular to these. So it's almost like adding up all of these little reflections next to each other gives the impression that those reflections are all one larger reflection. So you can kind of think of something like that causing that. And we'll see this in things like hair or anything else that has these linear grooves that are grouped together and moving in different directions. So you can see based on the direction of this hair that we're getting these different anisotropic reflections that are following perpendicular to the shaping of those hairs in these braids. Here's another example. We have just a matte plastic ball, which means our reflections are isotropic, which means it doesn't favor a particular direction. But in this case, this ornament has a fiber covering on it. It's almost like coated in these hairs that are linearly going from the top to the bottom. And you can see that's causing this anisotropic stretching of our reflections. And here's the effect on a shader if we're just taking the anisotropy value and we're increasing it from nothing, so it's isotropic, to fully anisotropic. And we can usually control in our shader the direction of this anisotropy. So in this case, we have a negative value, which is going to push the anisotropy or the direction of our reflections in the opposite direction. So here we can see in the positive, it's going horizontal, and then negative, it's going vertical. And you can control the shaping of this anisotropy reflections with something like a flow map or a vector map. So in this case, this is for like a game engine. So they're not going to simulate all that different hair, but they do want these reflections to kind of follow the flow of this texture map. So you can see we painted a hair direction on these objects. And so we want these reflections to kind of follow the shape of that hair that we painted. But the object doesn't have that information, right? That object is just a flat almost like you can think of like a plastic piece, right? So to get those reflections to follow it, we use things like a flow map, right? Which is going to kind of tell the application or the shader which direction the reflections are being favored for the anisotropy. So it's using a map. Usually you'll see something kind of like this where you have just two different directions and it'll be like a blue to red, and combining those two purple map where blue corresponds to the X direction and red corresponds to the Y direction. So it's telling on that surface essentially which direction to stretch the reflections or favor the reflections. And so you can think of it kind of like the wheel of a clock, the face of a clock, right? Where we have, as we blend between these different colors, it's telling the reflections to stretch in a particular direction, right? So it's just a combination of that blue and red color to give us these different directionalities. And you could also use a black and white map, right? Which black would represent 0 degrees, and then as we go to white, it's rotating around and favoring a different direction until we get to 180 degrees, which goes back to black. So you can use a black and white map to tell the reflections to point in a different direction. So you can see we have all these little this texture map here where it's just telling our anisotropy a particular reflection direction, right? As if there was like little linear grooves on the surface. And you can see this effect, right? It's stretching that light perpendicular to that direction caused by that black and white map. And this is really cool for things like, we'll see some examples of this, of getting a little bit more dimensionality to our specular reflections, right? Especially on a surface that has some kind of coating to it, or like an oil buildup. So in this case, we have this kind of smudgy, almost fingerprint-like texture map, right? And so all of these different blobs of color are just essentially telling the reflections to favor a particular direction, which gives this effect that it's almost like different layers of oil that are kind of pulling or tilting the light reflections into a particular direction. And here we can see that effect. It kind of has like a carbon fiber effect, which carbon fiber material will have this undercoating or this middle layer that has like this kind of fibrous directionality to it, which is what's giving these like particular reflection directions. And so we have all these different direction maps we can use to simulate these groovings or patterning on the surface to stretch our reflections. So as I mentioned earlier, having anisotropy can sometimes, depending on the material, it's not present in everything, give a little bit more dimensionality to our reflections. So here we have the isotropic reflections, and here we have the same texture maps, but we're also including an anisotropic reflection, which is giving a little bit more dimensionality and stretching to those reflections. And here we can see the same thing. On the right-hand side, we're just using a specular roughness map. On the left-hand side, we're using a specular roughness map and an anisotropy reflection, which kind of feels like it's been smudged. We have like an oil. On this one, it just feels like it's maybe just scuffed, right? So you can see how those reflections move across that surface in a little bit more of a complex way. Doesn't mean, again, that most materials are going to have anisotropic reflections, but it can be used strategically for different materials. The next thing we're going to talk about that's related to specular reflections, or it can fit under the category of specular reflections, is iridescence. So iridescence is an optical phenomenon where the hue of our specular reflections changes depending on our angle of view, which often causes a rainbow or pearlescent effect. So you can see over here, depending on the angle of view to the surface, we're getting different specular reflection coloring. So when I'm looking straight at the surface, you'll see we're getting like a pink reflection. And as the surface turns away from me, I'm going to an orange, to a blue, and then eventually to something like a green reflection. So you'll see this effect in nature on things like beetles, butterflies, hummingbirds, and fish, right? You'll have that kind of like shiny, shimmery, rainbowy, or pearlescent kind of effect on those creatures, which is due to iridescence. And you can see these things, this also on thin oil films on water or soap bubbles, and also on some man-made objects like CDs and DVDs. So here's some example, right? These are all more natural occurring phenomenon of iridescence. Butterfly wings, peacock feathers, certain minerals have a iridescent effect to them. And so iridescence, I'm not going to go into the specifics of this too much. You can follow this link if you wanted to, if you have access to these slides, to read a little bit more about it, what causes it. But it's most often naturally caused by the incident light, so light that's coming in, being modulated or amplified due to the multiple transparent layers reflecting light together to create interference patterns. So it's like you have a bunch of thin layers that are stacked on top of each other, and because of the different wavelengths of light, they're being bent or refracted differently as they travel through. So certain wavelengths of light are being slightly offset or slightly pushed in a different direction. And then when these layers are interacting or interfering with each other, those wavelengths of light are creating interference patterns with each other, which can cause some colors to be amplified and some colors to be essentially canceled out. So that's why when we look at it from certain angles, we get certain colors that are amplified and then certain wavelengths or colors of light that are being negated. This can also be caused by diffraction of light and things like CDs and prisms, but we're not going to talk about that. Okay, now we're going to focus away from specular reflections and talk about more advanced diffuse reflections. So remember, hopefully you recall from the first video that the diffuse shading component, or what we think of as diffuse, is an approximation of all the complex interactions that light undergoes beneath the surface of the object. So light that doesn't bounce off the surface, enters the surface and does a bunch of complex, crazy things and spreads out. And that's what we call diffuse, and that's a diffusion of light. Okay. For most materials, we use a very simple shading solution that simplifies all these complex interactions into an efficient but still realistic visual effect. So this is what we typically think of as diffuse. So opaque dielectrics most dielectrics are quite opaque, which means that light doesn't penetrate very far into the object. The diffusion of light is mostly very close to the surface. So light doesn't go very far, but it still spreads, very shallowly. Light doesn't bleed into the shadows, which we'll see this effect later on, which causes sharper details like these pores. You can see these pores in this rock, which is very opaque, which causes a very harsh and sharp look. And these objects generally feel more solid and dense. So most dielectrics that we've looked at and everything that would have diffuse or diffuse shading approximation are going to be these opaque dielectrics like stone, wood, a lot of plastics are like this, concrete, clay, dirt, right? So light doesn't penetrate very far underneath. And so we use that really simple diffuse approximation because it's cheap and efficient and gets the job done. Moving to the next category of dielectrics, we have translucent or transparent dielectrics. So translucent materials are dielectrics where light travels further through the medium before it's absorbed or reflected back out. So compared to the stone, which light doesn't go very far in before it scatters and reflects back out or is fully absorbed, translucent objects, light's allowed to go through deeper. So these objects tend to feel softer or more fleshy or waxy. If you ever look at something and it feels kind of soft or fleshy or maybe like a wax, then it tends to be a little bit more translucent. And this is caused by light bleeding into the shadow areas, which softens the appearance of surface details. So you can see this up here, right? We have light bleeding through the object or through these thin surfaces. And so these shadows have a softer look to them because there's a lot of light and color bleeding into them, right? Compare that to stone, which has that really hard, sharp, harsh look to it. And so here, in this situation, a simple shading approximation, which is the diffuse, what we were talking about earlier, isn't enough. The size and shape of the object has an impact on the shading of these materials, as does where light entering from one location and coming out another location. So we need to use more complex shader approximations or calculations to simulate these effects, where diffuse couldn't simulate these effects. The next category after translucency in terms of light depth scattering is transparent. So transparent materials let light pass completely through with minimal scattering absorption of light, and the image tends to travel through relatively coherently, which means the light doesn't spread or become clear or blurry or fuzzy. It comes through clear and all together, right? And so this is usually glass and liquids like water, right? This is what we consider transparent materials. So the effects of this light traveling through the surface of transparent materials is different enough from typical surface diffusion or diffuse that they also, like the translucent materials, it's different enough from diffuse that they need unique and usually more complex shading solutions and setups. So we have diffuse, right, which are very opaque solid objects. We have translucent objects, which are light travels significantly through the surface, but not all the way through usually. And it's usually the light that travels through blurs out and kind of bleeds around into the surface, giving us a softer look like the statue here, this marble statue. And then we have our transparent materials, which are like glasses and waters, which let light completely through for the most part. And here's kind of showing a visual demonstration of what opaque, translucent, and transparent means. We have these star images underneath the colors black, red, and white. So when you have opaque, the black, red, and white layer that's on top of the star is completely blocking the layer below. Translucent, we can see through the top layer a bit, but it's usually blurry. We're getting a lot of scattering, and then we're getting a lot of absorption still of light. And then transparent, you can mostly see a coherent or clear image through, and there's a lot less absorption of light in that top layer. And here's a visual diagram showing the effects of scattering and absorption. So scattering is the blurring of the image that comes through by scattering the light and ungrouping it as it travels through the medium. And absorption is going to be absorbing the light so light doesn't come back out of the system. And so down here we have very low absorption and very low scattering, which is like a, water, right? You can see mostly clear images coming through, and light is allowed to go all the way through and is not being absorbed and turned into a different medium, right? And as we increase the scattering of light, right, down here, the same amount of light's more or less still coming out of the system, but it's being spread across and out in different areas. So as light travels through, as it interacts with those particles or molecules within the material, that light spreads and is exiting from different locations, which causes a blurry image. It looks like it's very opaque or solid, but it's really just high scattering. And if we go up here, this wine or this dark ink, whatever this material is, it's still not scattering light quite as much, right? It's still going to have coherent images, but it's absorbing so much light that appears like a dark material, and a lot of that light's not allowed to escape. So some materials allow light to penetrate deeper or further beneath the surface than others. So just reiterating what we've talked about earlier, we are just talking about how some dielectric materials allow light to scatter further than other ones. So the point that light enters the surface and the point that light exits the surface can be far away. So here is light hitting the surface. We have all those complex interactions down below. And sometimes light might just go into the surface and come back out really close, right? But then sometimes light enters the surface, and before it comes back out, as it does all its complex interactions underneath the surface, it might come out at a location that's very far away from where it initially entered the surface. So if the size of the area that we're looking at is very, very, very large compared to that scattering depth, so that light, that distance that light enters the surface and travels and comes back out, then we are going to essentially treat that in a diffuse component, right? Which essentially all we're really saying here is when we're looking at a surface, that depth that light scatters is super low compared to essentially what we're looking at. So it's very unnoticeable in terms of how far that's scattering. So you could even imagine this actually being light that enters the surface, scatters around, comes back out. From far away, this looks like, essentially they're all coming in and leaving at the same point. So when that happens, for shading purposes, we assume that the distance is just zero, and the color is only affected by the light and provides surface color at a single point. So we don't worry about the entry and exit points, and this is when we use that approximation with diffuse. So we're using a simplified scattering kind of simulation with a simple formula, which is what we call, or what we think of as a diffuse shading component. And there's different ways you can calculate that and show that. However, if the size of our sampled surface is small compared to the distances that light travels or scatters underneath the surface, so here's that entry point, and here's where light might exit, right, which is a pretty big distance, and that area that we're worrying about is small compared to that, then we need to calculate how that light is actually traveling underneath the surface and exiting away from the original point of entry. So we need to start worrying about more complex subsurface calculations. And here we can see that light traveling enters at one location and exits at another location that can be pretty significantly far away from each other. And here's just another diagram showing that light interaction of specular and diffuse, right? So you have a light coming in. Some of the light just bounces off at the surface that it hits. And then the other rest of the light enters the surface and has these really complex interactions underneath it, right? Scattering, which means it's splitting and traveling in different directions. Absorption means it ends before it's allowed to exit back out, so it's fully absorbed. And then that diffuse reflectance is what we see as light that comes back out of the surface after it travels underneath. So that's that specular and that diffuse. And in reality, again, this is a very complex interaction underneath the surface. And with surfaces where it doesn't travel very far, we use diffuse, a diffuse shading component, and we're going to use different shading functions or calculations if that light travels very far and comes back out in a very far away location. There's different terminology that we'll use when we talk about this, and some of these terms can be used interchangeably for talking about the real world phenomenon of light traveling underneath the surface and scattering around and coming back out. So subsurface is a term you'll hear, so stuff that happens under the surface. Diffusion or diffuse, which is what we've talked about so far, that shading terminology, and scattering. So these can all describe the phenomenon of light scattering, refracting, absorbing throughout the material. So when you hear things like subsurface material or scattering material or diffuse material, some of that sometimes means that they have something very specific that they're talking about, but for the most part, they're kind of describing very similar phenomenon. So subsurface scattering is the term that we use for dielectrics that are more translucent than other ones. So remember, nearly all dielectrics are somewhat translucent because light is entering the surface, travels around, and scatters before it comes back out, right? So most of the time, that depth that light enters before reemerging is so small that light effectively can be thought of as entering and leaving from the exact same point on the surface. So we use a simpler calculation for these light interactions because it's so subtle. It's too subtle to need a physically accurate calculation effect. We can do a really cheap approximation and you won't notice the difference. However, some materials like skin, wax, milk, and marble are much more translucent than others and have a wider scattering distance. So we notice light bleeding deeper through the object, right? So like this wax candle in here, you can feel that light traveling through it and it gives it a softer feeling to it. So subsurface scattering is that term we use for the simulation of these light interactions beneath the surface when the distance from where light entered and exit is significant or noticeable. So if we're going to notice on the real world material that light travels deep through the surface, then we're going to use subsurface scattering instead of diffuse. So here's some examples on real world materials where that would be noticeable. So you have skin, right? Light traveling through, picking up and color as it's absorbed through the tissue and the blood underneath. We have this mineral, I'm not quite sure what it is, but it has like a jade or a marble-like feature, right? It has a lot of translucency, some cases transparency, but a lot of that light is still traveling through the surface and scattering and picking up a color. And then you have a lot of organic materials like food. A lot of food is translucent, right? And has significant scattering depth. So you'll see on like the flesh of fruit, like these grapes, light scattering it through the object and picking up that color and bleeding it into the shadow areas. And here we can see on this lemon slice, this lemon wedge, that even though as we move down, we're looking at the shadow side of this object, light is bleeding through those thinner parts into here. So we're seeing that light glowing through into the shadow side because it has a more significant scattering depth in that fleshy area than it does in the rind, which has a much shallower scattering depth. So the effects when we look at something that has subsurface scattering on it compared to diffuse are these. Right? First, you'll notice there's a softening in the contrast between light and shadow. That's one of the most significant parts that makes it look soft. So especially near the shadow's terminator, which we'll talk about or look at in a second. So essentially softens that transition between the light and shadow areas, which subsequently blurs and sometimes erases small surface details. So we'll notice if you look over here on this bun, right? Notice how when the subsurface turned off, which gives it that harder look, that a lot of these details feel sharper, crisper, and have that black shadowing, right? And so it gives it kind of like almost a crunchy or hard look. But you'll notice when that subsurface is turned on, that light travels through and softens and blurs out a lot of those surface details, which gives it a really soft and fleshy feeling to it. You can see that down here on whatever this sauce is supposed to be. When the subsurface turned off, we have these hard black shadows, and then when it's turned on, those shadow details almost completely blow out and blur away. We're also bleeding color into the shadows. So this is usually based on the color of the material beneath the surface. So in this case, this is actually quite inaccurate. But on this bun, you'll see there's like a orange-red bleeding through the bun material into the shadows. So the shadow where it was once black is now lightening, and it's also picking up an orange tint. Doesn't really make much sense for this kind of bun material, right? Because there's not like an orange or red kind of material underneath it. It's probably more of like a yellow tan color. This kind of gives it a weird fleshy look to it, like as if it has blood and flesh underneath it. So most likely they just use like an orange color. You'll also notice that on cheese, right? It's getting like a red orange color, which gives it like a fleshy look. Works well for the tomato because that's like a kind of a red orange material anyways, but looks kind of weird up here. And then the last effect we're going to notice is it causes light and color to reach opposite side of the model if the object is thin. So we'll see some examples of that, but if an object is particularly thin, light will travel all the way through the other side. So here's another example of those subsurface scattering blurring out our surface imperfections and details. So you'll see in these shadow areas that softening and that contrast between the light and shadow and that color bleeding is causing a lot of these surface details to blur away. And then we're using a subsurface color here. It's like a tan color, which kind of has like a flesh tone. So we're bleeding that color where it's a grayscale surface, but then we start to see this kind of like orangey brown color coming through. And so this is just a visual demonstration of what that terminator is. If you have a simple sphere or something that shades very simply like this, you have our light side. And as that light transitions to have less and less impact on the surface because it's facing the surface less, right? So as it hits an incident or at a glancing angle, right, more and more, less and less of that light is lighting that surface. And so that terminator is that transition into the shadow area. So on subsurface, when we have subsurface scattering on something, we're blurring or we're smoothing or reducing the contrast between that light side and that shadow side across the terminator. So some terminology you'll notice with subsurface scattering is going to be the depth or the radius. So this is how deep light is allowed to penetrate before being fully absorbed. So something like stone would have a very, very shallow or low depth or radius. And then something like skin or wax is going to have a much higher depth or radius. So that's how deep the light penetrates before it is fully absorbed or reflects back out. Color is going to be the color cues that are picked up as they travel through the light travels underneath the underlying surface. So you can see over here, as light travels through the surface, it's picking up like a yellow, orange, red, warm, fleshy tone. So that's going to be the subsurface color. There's two different components to subsurface scattering. There's going to be the forward scattering. So this is the effect of light hitting this front of a surface, scattering around and coming back out the front of a surface. And we're going to have backscattering. So that's light traveling from one side of the model and exiting out the opposite side or another side of the model. So you'll notice this over here, this is going to be backscattering. Light hits the back of the object and comes out the front of it. That's going to be backscatter. Front scatter is going to be light entering the surface, bouncing around and coming back out the front. And so that's where we're noticing that subsurface scattering affects the softening and color bleeding on the front. And here's a visual example of backscattering on a cat's ear, right? So if the object is very thin, light travels all the way through the other surface. Right over here, it's a little bit thicker, so we don't see light coming from the opposite side and traveling through and coming out this side right here. But over here, where it's much thinner, light actually comes all the way through. The scattering depth, we'll see we're increasing that depth and it's going to give it more of that subsurface look or more of that kind of fleshy or waxy look. So on the left-hand side, light doesn't travel very far. It still travels a little bit far, but not very far. And then over here, light travels very, very far, which is giving it a much more kind of gummy look to it. And here's just another example, same object or model, and we're just seeing light traveling deeper and deeper and deeper because as we increase that scattering depth. And here's just another visual example because I love showing lots of examples that I find. And you'll notice as that distance or that radius or that depth increases, you'll notice the light travels further and further and those shadows are disappearing, right? You see that shadow right there on her eyelid line. And as that light travels further and further, those shadows are letting light bleed through even more, which lightens them up, which means their contrast disappears. and it gives it, again, a fleshier and fleshier look to it. And you could use a texture map to control, right, where we have greater depth or scattering here on the ears and these areas like the nose and the lips and the eyelids, and we have less scattering on these more solid parts. And again, we're seeing that depth increase, and so we're getting a fleshier look, right? On the left-hand side, we're noticing a lot more of those details and pores and crevices, and over here, those soften out and disappear. So another term that we use besides depth is radius. So again, this is the distance light scatters beneath the surface. You can also find radius called something like the mean free path distance on modern or, the current subsurface scattering formula that we use. They'll use terms like mean free path, which can be used to describe how deep light, again, penetrates the surface. So here, down here, we have the same object, and we're just increasing that mean free path distance or that radius, and it goes from a hard, like harsh, thick plastic look to more of like a rubbery or thin plastic look. And the mean free path distance or radius or depth can also be stronger in a particular color. So for instance, you can tint it so that red light travels deeper and green and blue doesn't travel quite as far. So here in this case, we have the same kind of effect, but on the left-hand side, we're favoring the red color channel more so that you'll notice that red scatters into the shadow areas deeper. Whereas over here, the red, green, and blue all scatter the same depth, which means that we're not favoring a particular color. And here's another visual example of that. We have the same depth effects, or same depth setting that we have in terms of how far light's allowed to travel, but on the right-hand side, we're letting red travel deeper than the blue and green channels, which is giving us this kind of red orange tint right there in that shadow terminator area. From the light to the shadow area, here's the terminator. We're noticing more color bleed in the red channel. And we can use all kinds of different colors. We're often looking at fleshy colors, but you can see here we're getting a lot of we're using a mean free path or scattering color, which is giving these significantly different looks to these materials based on that color and that scatters underneath the surface. I like to bring up human skin as an example because it is a very complex, most things are very complex, but the human body is a very complex construction of many different materials and layers stacked on top of each other. So skin is composed of multiple layers, right? So we have actually different layers, the epidermis, the dermis, and the hypodermis. And we also have different materials underneath the skin, like we have fat, blood, we have different tissues, we have veins, muscles, bones. So these layers under the skin affect how deep the light travels underneath the surface and the color that is picked up or transformed as it travels underneath. So for instance, bone is going to be harder than skin, and it's also going to have like a yellow tinting to the color of the light. And then blood and tissue is going to be softer, so light travels further, and it's going to give a red-orange color. So because of this complexity, if you were to really try to simulate the light scattering underneath the skin, it would be an immensely complex calculation or simulation. And here's a visual diagram of just the skin layer, right? We have the epidermis, the dermis, and the hypodermis, which all have their own different components to them, which changes how light interacts with it. And if you're looking at certain subsurface scattering models, they might use like a 3-tiered layer system like this. Usually for skin, they have this 3-tiered system, whereas a lot of other materials, they might not separate, or you might not worry so much about the fact that it has multiple layers. But this 3-tiered subsurface scattering model is often used for particularly skin, which has that shallow, middle, and deep scattering, and each of those scattering layers are scattering different colors because of that different composition at each of those layers. And because of that, the light is traveling different depths, and different wavelengths of light are allowed to travel at different depths because they're scattering or being absorbed by different materials. So you'll see usually maps for those kinds of subsurface shader models like this, where you'll have like your diffuse layer, which is the top dermal layer, and then you'll have these different layers for changing the color of light depending on how deep it goes, right? So you have that second layer right here, and then you'll have that deeper layer. So again, that softness of materials that are more translucent that soft look comes from the light scattering greater distances beneath the surface. So here we have an example of a statue, and we're just increasing the distance or the depth. And so that softness of it, that kind of fleshy or just soft feeling to it, is caused by that light traveling through. When it doesn't travel very far, we have these really harsh shadows. It feels very hard and it feels very solid. And over here, it feels a lot less solid and soft. So the shadows are less harsh due to the light traveling into the shadow areas and blurring that transition between the light side and the shadow side, which is that terminator. The more translucent the object is, the more light will bleed into those shadows, picking up local color as the material beneath the skin absorbs different wavelengths of light. So again, we have a skin material or skin example, and you'll see a lot of skin examples when we talk about subsurface scattering, because that's one of the most common uses of the subsurface scattering shading property, is to simulate the more complex skin interactions, right? And so we're seeing that color bleeding of orange and red into those shadow areas. And if you were to look at the skin or similar materials with no subsurface scattering on it, you'll notice how porous or hard or harsh the surface can look, because there's a lot of detail and imperfections on the skin, right? And on a lot of surfaces. But because of the translucency of the skin, we don't notice a lot of those details, right? They blur out because that light bleeds through the surface and softens the look of those bumps and craters that we see on the face. Something that's important to note is that specular reflections aren't usually affected by subsurface scattering, because remember, subsurface scattering is the light that enters the surface. Specular is the light that bounces off the surface. So those are two separate shading interactions. So even though the subsurface can make those shadows appear soft and blurred out, right? Specularity can still make those details pop and feel sharp and crisp, because that's just a different shading interaction, right? The light isn't traveling through the surface, it's bouncing right off the surface. So as a final reminder, subsurface scattering is simulating the same light interactions that diffuse shading component is, but we're using a more advanced calculations. So we use subsurface scattering when the distance that light travels beneath the surface is noticeable. So if it travels significantly far beneath the surface and we notice it in real life, we might want to use subsurface scattering. Diffuse is used for most materials, most dielectrics, which are usually much more opaque. So most dielectrics are fairly diffuse or opaque, and the distance light travels beneath the surface is so small that we can use a simplified shading solution. And some final notes on subsurface scattering. The scale of your 3D object is very important. So you will want to make sure your scene file is using the correct units and your object is scaled appropriately, because subsurface scattering and how deep light scatters beneath the surface is very, real world units dependent. And so if you have the same model that's really tiny versus the same model that's really large, that effect of light scattering underneath the surface is going to be different between those models. Subsurface is very expensive to calculate versus diffuse, so try to limit how often you use it. Most dielectrics that you're going to have are not going to need subsurface scattering. The effect is so small or unnoticeable that you should just stick to diffuse to save on costs. And objects that are very large or very distant usually have a reduced subsurface scattering effect. So if you had like a really, really, really large human, for instance, like a giant, and you were viewing them from far away, relative to the size they are and the distance you're looking at them, that subsurface scattering effect might be a lot less noticeable. Okay, moving on to our last dielectric shading component effect that we're going to talk about is transparent materials or glass-like materials. So glass-like materials or transparent materials are unique in that they do not strongly absorb or scatter light like other dielectrics. So light can pass almost completely cleanly through from one side to the other. So we usually call transparent materials glass-like, and so you'll see a lot of shader parameters using terms like glass, right? And so that's going to be the categories of things like water or crystal or gemstones or glass. So what is more noticeable with transparent objects is the effect of refraction of light, or the bending of light as it passes from one medium to another. So as it goes from air into the glass or into the water. So in our rendering program, we usually define a glass material by a couple parameters. One is how much light is transmitted through versus how much is absorbed. which colors of light are absorbed or transmitted. So whether it's favoring a blue or a green. So something like apple juice is going to absorb all the different colors of light besides like a warm red or orange color, giving it that orange look to it. How much light is scattered as it travels. So something like a milk, right, is going to scatter a lot more light through it. And in that case, we might think of it more like translucency instead of transparency, but it doesn't matter. And so we think of that as the roughness of the light refracting through. So it scatters. And how much light refracts as it bends, right? So some materials like a glass are going to bend light a certain percentage, but then other materials like a diamond are going to bend light even more. So again, here's that kind of chart that I was showing earlier, the scattering versus the absorption of transparent materials. And again, once you get to high scattering, you might think of it more like a translucent material. And so here's another example showing a prism, right, or a glass block, really, where we're shooting a beam of light. And because of the material, the refractive properties of this block of glass or whatever it is, you have light bending and changing direction. And then once it leaves and goes back out to air, it bends again. So going from one medium to the next, where you have a bending of light and changing of direction. So this is calling back to what we had talked about with specularity and index of refraction. So index of refraction, as a reminder, affects how much light is reflected off of the surface. But now we're talking about how much the index of refraction is changing how much light bends as it travels through. So here we have air and we have water, which have different index of refractions. And so indices of refraction, I think. And so you can see this angle that it's hitting at relative to the surface is 30 degrees. But then, and that water is going to cause it to bend in a different direction. So it bends slightly as it travels through instead of coming in as a straight line. And so water has a higher index of refraction than air, right? Which causes the bending of light that we just talked about. And then if a material has a greater index of refraction, like a diamond, which has an index of refraction of like 2, then it causes a more significant bending of light. So if the index of refraction between these two materials, air and water, are closer to each other, then it's going to bend a little bit. But then if the difference between those two materials is higher, the index of refraction, then it's going to bend a lot. And so the index refraction is the material property that drives how much light will bend or refract. And the effective refraction is greater if light is leaving one material and entering another where the difference is large. So you'll see as that index refraction increases, we're going to get greater and greater bending of light, and that medium is going to be denser, right? So we have like water, which is 1.3, but then diamond is greater than 2, which is going to reflect more light and bend more light. So index of refraction, again, determines how much light bends as it travels to the surface. So here we have a very, very thin material, or a material that has index refraction material property that's very similar to air. So we're not bending that much light. And you'll notice, look at that grid pattern in the background. As we increase that index of refraction, more and more of that background is being distorted and warped as it travels through that object. Index of refraction, of course, is also more noticeable when light is traveling through a thicker medium. So glass and water actually have very similar index of refraction, but in this case on the left-hand side, we have essentially a solid object of water/glass. Over here, we have two very thin objects of glass. So because there's a lot less of this material it's traveling through, we're noticing a lot less bending of light. We're still seeing some bending, right? You can see where the finger separates right there. So it's still bending the light as it travels through, but it doesn't travel through very far. But over here, it's traveling through a very thick medium, which is giving almost like a flipped image of this person on the other side. It's not actually flipped, I don't think, but you'll notice that light is bending and changing a lot. So one of the other properties we're going to think of with glass is going to be roughness, which can be the roughness of reflections, but in this case, it's going to be the roughness of our refracted light. So this is how much light is scattering as it travels through. Again, going back to that chart, think of this as like water, which has very low scattering, and think of this as something closer to like milk, right, which has a very high scattering. So that image that comes through is not very clear. This is not changing the bending of the light, right? So these might be having the same exact refractive components to them, but the light that's coming through is scattering as it travels through. So the light is spreading or separating from each other. We might have a glass color, which is going to be the different absorption of different wavelengths of light. So In this case, with something like water, it's not going to have very high absorption, or it's not going to favor a particular wavelength of light. But then something like, let's say, Kool-Aid or Gatorade, right, is going to be reflecting certain wavelengths of light, which gives it a prominent color. And as a reminder, referring back to our specular reflection talk in the previous video, the index of refraction can also determine how much light is reflected off the surface. So that same property that's changing the bending of light can also change how much light is reflecting. So the higher the index of refraction is, the brighter our reflections are going to be. And here's just one bonus shader property that I kind of wanted to mention because it comes up surprisingly frequently, which is emissive materials. And so an emissive material is going to be a material property that causes your object to actually create light. So most materials in the world are not going to create light, right? Only certain chemical reactions create light. You know, if you have like a halogen light bulb, right, the material property and that excitement of that material through electricity creates light, right? Creates photons of light. But most materials are just reflecting or absorbing light, right? They're not actually creating more light. But some objects, like phosphorescent or bioluminescent materials, are going to actually create light. They're going to convert energy, some form of energy, back into light and emit new created light. So when we think about, when we deal with emission, it's a pretty simple, straightforward property, and you're going to know exactly when you're going to want to use it. But when we think of emission, we're going to think of just these two material properties. One, it's going to be the intensity, so how bright or how much light is given off by it, and then the color of that light that is being emitted. When you're doing something like emissiveness, usually when we think of like surface color, we're thinking of values in sRGB from 0 to 255. So colors are just going to be that friendly to read for computers and monitors, that 0 to 255 pixel color range that we work with, right? Or you might have a value from 0 to 1 if you have like a normalized color range. And so that's where most of your colors safely sit in. And also things like specular reflectance or any other material attributes are going to sit between a 0 to 1 range. But because lights often work with values of exposure, right? And so we're going to kind of, we usually don't have like an upper limit in terms of how strong or intense that light source can be or how much light we can emit. When we deal with shader properties or texture maps that are related to emission, we might want to push it further than that 0 to 1 or 0 to 255 range so that we can increase the amount of light the surface emits. So just keep that in mind, that if you are working with something that's glowing or emitting through a material, you might have to push those values higher, or watch out for things like clamping, where certain nodes in your rendering software might want to clamp the values to a certain value. And so here's just one example I would show of an object that has a simple shader on it, and then you'll see these cracks are essentially emitting light. So in some cases, we're actually emitting light, like if you're using an offline renderer like RenderMan, Arnold's, or V-Ray, you're going to actually create light, right? You're going to actually simulate light shooting off that object and interacting with the environment. But in the case of something like a game engine, right, or a really light inefficient shader, you might think of that emissiveness or that emission of light really as shadowing or lighting the shadow areas so that shadow has less of an impact, right? So because it's emitting light, those shadows are brightening in there, right? So in certain shaders, that might be more of a fake or a simulation. So that's all I wanted to talk about for this video, just to follow up and explaining on more advanced shader principles that you might run into, particularly when we're dealing with glass and subsurface properties, which you'll encounter and you'll have to worry about.